Okay, so for today's lecture, we'll start with lacing and battening for built-up compression members. Okay, if you look at this photograph, here it is showing a lacing system. Okay, the first one, if you look at this is called single lacing system. This is called single lacing system. So what is this? These are the two columns. If you just look at this, say you have two columns with two I section, so they are built like that. Fine. Now what we need to do? We need to provide lacing. Where we can provide the lacing? Lacing we can provide on the flange part. Okay, we cannot provide at the web. So in flange part we are connecting with the lacing systems. Okay, if you look at this will look like that. Yeah, if you just look at this side, it will look like that. If you look from this side, these are the inclined members, so it will look like that. Okay. Now what we can do? We can do in one directions like that we can provide, or we can provide in this direction also. These systems, whatever I have shown here, it is called double lacing systems, and this system is called single lacing systems. Okay, so depending on that how you are designing it, you can design as a single lacing system, or you can design as a double lacing system. Okay, now question is how to provide the lacing. Okay, so what are the guidelines to provide the lacing systems? Okay, the simple guideline is that whenever we are providing a lacing system should be provided in such a way that, what I need to say, this is the, just look at this photograph, then you will understand. So this is what I have shown here is the same lacing systems here. In these systems what I am showing, so these are the two columns, this is one column and this is another column, and the lacings are provided on both sides of the flange uniformly. Whatever you will provide on this side, the same things is to be provided on the other side. So these are the lacings are provided. Okay. Now how to provide the lacing, that a guideline is there. This is the basic guideline that you need to. What is saying that the compression member comprising two main components. These are the two main components. Lacing is given. Where practicable, have a radius of gyration about the axis perpendicular to the plane of lacing. So this is the axis which is perpendicular to the plane. This is the plane of lacing, and this axis is perpendicular to the plane of lacing. Okay, that means this axis will have a radius of gyration ry. Okay, not less than the radius of gyration at right angles to that axis. Not less than the radius of gyration at a right angle to the perpendicular axis. So this is the perpendicular axis to the lacing and right angle is this. That means the axis which is parallel on the plane, the axis which is parallel to the axis of, you can say, lacing. Okay, so that radius of gyration is Rx. Okay, what it is saying? It should not be less than. Okay, Ry should not be less than Rx. It means at least Ry should be equal to Rx. Okay, or it can be greater than. As far as possible, for an economical design, we will try to design that Ry should be equal to Rx. Okay, so this is the basic criteria that we need to follow for design of a lacing. There are some other guidelines are given in the code book. We will see them one by one. Okay, so again I will go back to the first photograph, whatever I have shown you. So in this photograph, what I said, this is a single lacing system and this is a double lacing system. So whatever the way, if I draw this one, and if you just reverse it, or otherwise I can draw it in other way also. So this is the column and this is another column, and on the edge of the other side, what I am doing, I am drawing the lacing. So this lacing, say, it will look So this is the lacing, and if I draw the axis of this is the x-axis, and this is y-axis, and this is, so this is what I can say, this is y-axis, and this is x-axis. Okay, so guideline is saying that ry should not be less than r. So, okay, so here what we are looking from this side, basically from this from top. If you are looking from this side, or if you are looking from this side, say we have a lacing here also, in this side also there must be a lacing. So lacing is to be uniform in both sides, whatever the side we are using, same thing. Okay, so if you look at this side, it will be looking like that. So it may be a single lacing system, or it may be double lacing system. So what do you have to do? You have to find out the radius of gyration about y-axis, that is perpendicular to the axis of lacing and parallel to the axis of lacing, and you have to check it. Okay, so here the same thing. Now for the design purpose, the first put guideline, if you refer to the code book, in the code book, if you refer this clause number 5.7.2.1. okay, in this clause it is given that how much load that is to be taken care by a lacing. Okay, whether it is a single lacing system or double lacing system. Okay, so that is basically called the shear, design shear, that is shown here as B, or if you look at this is shown here as B. Okay, so in a lacing, this B value is equal to 2.5% of the design load. That is, if you are applying the axial load on the column as P, then 2.5% of the P will be considered as the design shear for lacing systems. Okay. Any other lateral loads, if it is coming, say wind load or anything, so that is also to be considered in addition to this 2.5. So the B value will be in addition to that. Okay, if there is no other type of load, then the B value will be equal to only 2.5% of the P. Okay, now come to the next part. So if we look at these systems, that means in lacing systems we have to provide the lacing in inclined directions. Okay, so look at this. This is the vertical axis and this is the inclined axis. So if you look at this left one, then this is the vertical axis and this is the vertical axis, and these are the inclined axis. So if you see, the inclined axis is making some angle with the vertical axis. So here if you look at this, inclined axis is making some angle with the vertical axis. This is denoted by theta. So this theta is nothing but the angle of inclination of the lacing with the longitudinal axis, and this theta range from 40 degree to 70 degree. Okay, so remember it, this theta is ranging between 40 degree to 70 degree. Okay, so that means what we can say, theta cannot be less than 40 degree and theta cannot be more than 70 degree. हेलो, हाँ बोलिए। हाँ, मैं आधा घंटा बाद कॉल करता हूँ, मैं अभी एक क्लास ले रहा हूँ, हाँ, ऑनलाइन स्टूडेंट, ठीक है। हाँ। कहाँ था यार, pause, हाँ, something. Okay, so what we can see that theta should not be less than 40 degree and theta cannot be more than 70 degree. Okay, so this is the range of this angle theta. So one is the design shear, second is the theta. Okay, now for the design purpose, what we have to do? We have to find out the slenderness ratio. Okay, that we have seen earlier also. The slenderness ratio is to be calculated for any kind of compression member. Here also, since this is a part of the compression member, this lacing, so we have to calculate the slenderness ratio of the lacing, and there is some limits given in the code book. What is the limit given in the code book? Let us see that in the code book. If we go to the clause number 5.7.2.3, okay, if you go to clause number 5.7.2.3, the limit is given. Limit is saying that the slenderness ratio of the lacing bar should not exceed 145. Okay, so slenderness ratio, that is denoted by lambda. What is lambda? Lambda is equal to effective length, right? Effective length divided by radius of gyration of the lacing bar, that is lambda, and this value cannot be more than 145. Okay, so this is another guideline. Guidelines is saying that the lacing slenderness ratio should not be more than 145. Now the question is how to find out this effective length. Okay, let us do it quickly. For single lacing system, that is I am talking about the first one. For single lacing system, the effective length is taken like that. The effective length between inner end rivets on the lacing. That means suppose we are using riveting system, then from this point to this point, whatever be the length is there, that length is called effective length. Okay, so if there is, say, two rivets are there, then the inner side one. If it is single rivet, then the center to center of the single rivet. Then whatever the length is, that is called the effective length of the lacing bar for single lacing system. Okay, now come to the double lacing system. In double lacing system, the effective length is equal to 0.7 times 0.7 times center to center distance of the inner end rivets. Okay, that means in double lacing system also, this one, center to center distance between the inner end rivets. Okay, and then we have to take 70% of that, so that will give you the effective length. Now in case of welding system, it's the same thing, that is 0.7 times the distance between the inner end of the effective length of the weld. Okay, so 0.7 times distance between the inner end. Suppose if you have some welding up to this part, then from this portion, so this is the welding to up to this portion, so this will be the length of the length, and then this length is to be taken as 70% of this length is to be taken as the effective length. Okay, so this is how we can calculate the effective length of the lacing members. Once we know the effective length of the lacing member, then we can calculate. But before calculating that, before calculating the lambda value, let us know what is the dimensions of this lacing bar. Dimension of lacing bar means what will be the cross section of the lacing bar. Let us take the cross section of the lacing bar. So this, okay, so that means if this is the cross section of the lacing bar, what we need to know? We need to cross section. Here I am cross section means I am talking about this one. If we just cut it here, then this is what I am talking about, right? So this will be, this is denoted by B, breadth of the lacing bar, and this is denoted by thickness of the lacing bar, T. Okay, T is denoted as the thickness of the lacing bar, and B is the breadth of the lacing bar. So if you take anywhere the section, okay, so this part and this part, okay, B and T, this is B breadth and this is thickness. Thickness is denoted by T. Let us assume this like that. Okay. Then we will see what is the limit or how to calculate the B and T. Now before that, our objective is to know the lambda, calculation of lambda. Okay. So what is known to us, that lambda is equal to L effective by radius of gyration. What is the radius of gyration? Radius of gyration is nothing but equal to root over I divided by A. What we want? We want maximum radius of lambda. Maximum lambda means minimum radius of gyration. L effective divided by. What is I? I is the moment of inertia of this section. So if you take the moment of inertia of this section, what will be the moment of inertia of this section about its center? That will be B T cube divided by 12. Divided by its cross section area. What is the cross section area of this section? B into T. So B get cancelled. What is left? So I am writing here. What is left? Left is L effective root 12 divided by T. This is the slenderness ratio of a lacing member, and this value should not exceed, as per the Kudal's guideline, this value should not exceed 145. Okay, fine. So now we know how to calculate the slenderness ratio. Okay, both the direction you find out. It may be RYY direction also, RXS direction also. Basically, in case of a lacing member, it should be in only one direction. When we are talking about the full column member, then both direction you can find out, in YY direction also, in XS direction also. Now let us see that part. Okay. Now the codebook is saying that. Okay, no. Before going that, let us know how to decide the B and T. Just now we had a talk about B. So B is the breadth of the lacing member. How to calculate that? That guideline is given in the codebook. If you go to the codebook and clause number 5.7.3, clause number 5.7.3, the breadth of the lacing member, guideline is saying that it depends on the diameter of the rivet that we are going to use. Okay, guideline is given like that, whether you are using 20 mm dia rivets or 22 mm dia rivets or 18 mm dia rivets or 16 mm dia rivets. For these various diameter of the rivets, the minimum breadth we can take as 65, 60, 55 and 50. Now this is the guideline given that depending on the diameter of the rivet that we are using for the lacing system, the minimum breadth in terms of mm is given in the codebook. For 22 mm dia rivets, it should be 65 mm. For 20 mm dia rivets, it should be 60 mm. For 18 mm dia rivets, it should be 55 mm. And for 16 mm dia rivets, it should be 50 mm. Okay, so this is how we can choose the breadth. Now next part is we have to choose the thickness of the lacing bar, whatever, whether it's a single lacing system or double lacing system. Okay, let us see how to choose the thickness of the lacing bar. Thickness of the lacing bar is given in next clause, that is clause number 5.7.4. Clause number 5.7.4. 5.7.4. Okay, if we refer that clause, it is saying that the thickness of the lacing bar T should not be less than L upon 40. Okay, for single lacing system, and it should not be less than L upon 60 for double lacing system, or we can say welding at intersection, riveted or welded at intersection, whatever. And in this way it may be riveted, it may be welded, but the thickness in this case should not be less than L upon 60, and thickness in this case should not be less than L upon 40. Now what is this L? L is the center to center distance from the inner end rivets or weld. Okay, so this is how we can decide what should be the minimum width of the lacing bar and what should be the minimum thickness of the lacing bars. Okay, so once we decide that, then next part is to decide the spacing, that is this L. This is the spacing. Okay, from this rivet end to this rivet end, or from this rivet to this rivet end, what is the distance? Okay, how to calculate this? Let us see. Now if you go to clause number 5.7.6, 5.7.6, in clause number 5.7.6, a guideline is given that the spacing of the lacing bar shall be such that the spacing of the lacing bar shall be such that L divided by RC minimum, L divided by RC minimum shall not be more than 50 or 0.7 times the maximum slenderness ratio of the compression member as a whole, whichever is less. Okay, maximum 0.7 times maximum slenderness ratio of the compression member. So this one I am saying maximum slenderness ratio of the compression member as a whole, whichever is less. So out of these two, whichever is less. Okay, so guideline is saying that L divided by RC minimum should not be more than minimum of 50 or 0.7 times the maximum slenderness ratio of the column member. Now there are two new terms came. One is this RC minimum and another is the lambda C max. What are these two terms? Okay, let us see. What is this RC minimum? What it is, from the name itself it is saying that it is talking about the column. Okay, this is basically the minimum radius of gyration of the components of the compression member. That is the whatever be the column you were using earlier. For this column member, what is the minimum radius of gyration that we need to calculate? Okay, we need to know what is the minimum radius of gyration of the column member, and that value is to be taken here. Minimum, not maximum. Okay, minimum may be in y direction, minimum may be in x direction, so you have to take the this value. Next, what is lambda? This is what we are talking about, the maximum slenderness ratio of the compression member. So for this column member, what is the maximum value of lambda? If we are giving a symmetric, in that case, or that what I said, radius of gyration in both directions will be equal, so the lambda will be equal, otherwise lambda will be different. Okay, so you have to find out what is the maximum slenderness ratio corresponding to the minimum radius of gyration, and that two value you have to find out, and then multiply this with 0.7 this or 50. Check which one is minimum, that you have to take, and then L will be equal to minimum. L will be equal to whatever be the value, or L should not be more than, not minimum, sorry, L should not be more than, what is that? That value, whatever the value is coming, say the value is coming x, then x multiplied by RC. Okay, so based on that we can find out that what should be the maximum value of L, and then you choose maybe little bit less or little bit less value of that, or the up to value of L, and we apply. Okay, then our next part is the how much force. Basically we need to check the end connection, whether say system is okay or it is failing, whatever the dimensions we have decided till now. So how to do that? We have to check how much force that is going to act on a lacing bar, whether it is a single lacing or double lacing, doesn't matter. Okay, but we have to find out that how much force each of these lacing bar is facing. So that force here is denoted as by F. If you see, or if you see here, it is denoted by F. This F is the force which is acting on the lacing bar. Okay, so how to calculate this F? So as I already told you that this shear B is equal to 2.5% of the applied load P. Okay, so the force this F is basically shared equally among the two parallel faces. This is one face and in the other direction there is another face. Okay, that means what it is saying is that if you take this and if you cut it, so this will be one face and this side will be another face. So it will be divided equally. That is 50% in this side and 50% in the other side, right? So what is shown here is, that means you say this is your this member, lacing member, and this is the force. It may be compressive force or it may be tensile force, doesn't matter. And then this is say your shear. Okay, similarly out of this B, this side will be 50% and that side will be 50%. So you can say B by 2 here, simply we can say, and that side will be, if I draw it, so this side, if this side is B by 2, another side also will be, okay, B by 2. Now what is the F? How to calculate this F? What is the relation? That since this angle is theta, so what will the F is? F will be basically equal to B by sin theta, or what we can say, B is equal to F sin theta. But since it is equally shared between the two faces of the plane, so F will be 50% of this. Okay, so F will be equal to B by 2 sin theta, right? And this may be either compressive or tensile, depending on how your B is. B is like in this direction, outward direction, tensile, then this F will be tensile. If B is compressive, then F will also be compressive. What will happen to the double lacing system? In double lacing system, this F is divided between the two lacing bars, so it will be another half. That means this, if this is for single lacing system, for double lacing system, say I am denoting as F1, for double lacing system this will be half of this, because it is again divided into two lacing bars, so this will become 4 sin theta. Okay, so now we know how much force each of the lacing bar is facing. Each of the lacing bar is facing. Okay, so once we know that, then we can, what we can do, suppose if we have a compression member, then the force is compressive force, or if this is tension member, or if this shear is under tension, then it will be a tensile force. Whatever the force, we know what is the maximum compressive force and what is the maximum tensile stress, and what is the maximum compressive stress, that is known to us, and we can find out how much compressive stress or the tensile stress that acting on the lacing bar, and we can compare this with the limiting value. Okay, so let us just quickly do that part. Okay, so what I am, suppose if we have a compressive force, okay, then what we need to know, we need to know what is the compressive stress. What is the compressive stress? Force divided by cross section area, force divided by gross cross-sectional area of the lacing bar, because we said the lacing bar is B and T. B is the breadth and T is the thickness. So this, okay. So what is the limit? We know that in case of compression member, the limit is sigma FC. Okay. Now we know what is the lambda value of the lacing bar. Already we have calculated, and the grade of the steel is Fe250. So from the code book you find out the value of sigma FC. Find out this ratio. Check that this ratio should not be more than sigma FC. Then you can say in case of compression, in case of compressive force, this is okay, accepted. If it is a tensile force, the way I have shown here, if it is a tensile force, then what will be the tensile stress? Tensile stress is what? Force divided by net area. Okay, so what will be, suppose if we here we have a one rivet. So what is the net area available? B minus the net length multiplied by the thickness, and this should not be more than sigma 80. Right? That is sigma 80 is how much? You know, already discussed. That is 0.6 times of F1. Okay. So F divided by B minus D to T into, and this value should not be sigma 80. Check that in case of tension. If both the cases our design is satisfying, then we can say we have done a safe design for the lacing bars. One, we have designed the lacing bars, then we need to find out the, basically we need to design the end connection, that is number of rivet required or welding required, whatever we have. Okay. Now for the end connection design, we need to find out the number of rivets required. Number of rivets required is equal to force divided by rivet value. Okay, just before that, let us see, there are two ways how we can provide the end connection. This is the figure 1 is showing the one way. See, this is connected like this, this is connected. So two different rivets we have used here, and this is another way how we can provide. That means what we are doing, we are just overlapping one lacing on another, so we are saving one rivet. Here we cannot save. Here what we are doing, we are simply providing the this lacing in this way. So we are providing two rivets. Okay. So there are two different arrangements are there. So for these two different arrangement, how we can provide them for a kind of A class A. So this is a type of arrangement type A. The number of rivet required is equal to force divided by rivet. We know how to calculate the rivet value. So this will give you the number of rivet required. For case B, when the second category type of the arrangements are there, the number of rivet required will be equal to 2f cos theta. 2f cos theta divided by rivet value. Okay. So in this case, number of rivet required will be f divided by rivet value. So number of rivet required will be, in this case, this one. And this is the second case. For that, the number of rivet required will be equal to 2f cos theta divided by the rivet. Okay. So this is how we can design the number of rivet required. Now if you are doing the welded connection, then how? So we are doing lap joint. Lap joint, you know that overlapping, when that is basically this case, when we are overlapping the lacing bar like that. When we are overlapping the lacing bar, or when we are providing butt joint, then one lacing bar will be this way, and then another lacing bar will be there, and we will do the connection. Okay, here using the butt joint. Okay, so in case of lap joints, the guideline is saying something like that. You just can note down. The overlap should not be less than, this overlapping should not be less than 1/4 times the thickness of the bar or the member, whichever is less. 1/4 times the thickness of the bar or the compression member. 1/4 time the thickness of this bar or the compression member, whichever is less. Okay, overlapping should not be 1/4 time the thickness of the lacing bar or the thickness of the compression member, whichever is less. Okay, in case of butt joint, if we do the butt joint, in this case full penetration part weld or fillet weld on each side is to be provided. Lacing bar should be placed opposite to flange or stiffening member of the main member. Again I am reading, the lacing bar should be placed opposite to flange or stiffening member of main member. So this is how the lacing design is to be carried out. Okay. After lacing, then we have another member that is provided in the column, that is called battens. So in our next lecture, we will see how to design the battens. Once I complete the design of battens, specifically the guideline, then we will take an example and we will see quickly how we can apply those concepts for in actual design of a column using the lacing and battens. Okay, just wait for the next video. I will upload, and then we'll see how to apply this concept for a design.